Hi, this video introduces expected time efficiency. This is a concept that we'll need to have defined as we go into analyzing how hash tables work and also just understanding the concept of how the hash functions work and distribute keys into different array elements. So first, let's recap the kinds of efficiency classes we've seen so far. There's a worst case kind of efficiency class. For example, big O of 1 worst case time. That means that every single time you run an operation, it's big O of 1. That's what worst case means. Big O of 1 amortized time is a variation on that. Amortized is kind of like a qualifier or a tag. It means big O of 1 is a little bit different from usual. Big O of 1 amortized time means that the operations take an average of constant time over a sequence of n operations. So some individual operations actually are not constant time, but if you run enough of them and average it out, then on average each operation is constant time. And we saw that with vectors. When you add an element to the back of a vector, occasionally we have to resize the vector, and so that's why that is a constant amortized time operation. What we're introducing now is another one of these qualifiers or variations called expected time. Big O of 1 expected time means that the expected value of the time complexity is big O of 1. Expected value is a concept from probability or statistics that says basically what the weighted average of a random variable is. And in our notation, unless we say otherwise, an efficiency class is assumed to be worst case. So if you just say big O of n without any qualifiers or explanation, we take that to mean big O of n worst case. So often we just write efficiency classes without specifying worst case amortized or expected, but if a efficiency class is amortized, we have to add that word to be clear. If an efficiency class is expected, we have to add that word to be clear. And then sometimes we write out worst case to be crystal clear that an efficiency class is not amortized or expected. So let's review what an expected value is. If you've dealt with this in another class, you know all about expected value. If not, this will be kind of a quick introduction of the concept of expected value. First, we have a notation for a probability. PR bracket x means the probability of x. That denotes the probability of event X occurring. So the idea is that what goes in between the brackets is a description of some kind of event that may or may not happen, and PR of X is the probability or likelihood in a quantified way of that event occurring. So for example, you could say something like the probability that a binary search tree is balanced. Maybe if we inserted the elements into a tree in random order, we could define the probability that that tree ends up being balanced, and that would be a probability number. Probabilities are always fractions in the range 0 through 1. So 0 means no chance at all, like a 0% chance. A probability of 0.83 corresponds to an 83% chance, pretty likely but not sure. And a probability of 1 means a 100% chance it's certain to occur. A related concept is the expected value of a random expression or variable x, and it's written E bracket x. E is for expected. And the basic idea of the expected value is that it's the weighted average of all the possible outcomes of event x. So if x is a random event that has n different possible outcomes, numbered x1, x2 through xn, and the probabilities of those outcomes are p1, p2 through pn respectively, then the expected value of x is this summation. We sum up for every event number I, xi times pi. So the outcome value, xi, multiplied by the probability that it occurs. And when we add up all of those, we get what's called the expected value of x. It's basically the weighted average of every possible outcome of the event. Here's a concrete example. Let's look at one of those scratcher tickets. Those are those little gambling tickets where you scratch off some foil and it tells you if you won anything. Usually you don't win anything. So let's say these are the three possible prizes you can win on one of those tickets. Let's say there's a 6% chance that you win $5, a 1% chance that you win $100, and a 0.02% chance of winning $5,000. Very unlikely to get the jackpot there. So let's say X is the random variable of how much you win, your winnings on the ticket. Then the expected value of x would be the sum of every possible outcome multiplied by the likelihood of that outcome. So that would be $5 times 0.06, because 6% converted to a fractional decimal is 0.06. So that's the expected value of the $5 outcome, plus there's a 1% chance of 100, so that's 100 times 0.01, plus there's a 0.02% chance of $5,000, so that's 5,000 times 0.0002. And if you do out that arithmetic, this comes out to 2.3. So we would say the expected value of this ticket is 2.3. If these are dollars, that means that on average you can expect to win $2.3 if you average this out over many random plays. And so the gambling company would probably sell this for more than $2.3 so that they make a profit. They might sell it to you for $5 so that they tend to uh, tend to profit on these. So the application of this is to randomized data structure operations. A randomized algorithm is a algorithm that deliberately makes random choices at runtime. For example, it calls the rand function, which returns a random integer, and uses that random integer to make some decision about what to do next. Some data structure operations are randomized. They have a random element to them. They make random choices at runtime, and that impacts how fast they run. Notably, hash tables. That's why we're introducing this right now. So the number of collisions in a hash table impacts its time efficiency. The more collisions you have, the slower you can expect it to run. The way that they work is they have a randomly chosen hash function. And so the number of collisions that a hash table experiences is a random variable. Again, you could be lucky and get a good hash function for your set of keys and have very few collisions, or you could be unlucky and get an unfortunate hash function that creates a lot of collisions for your set of keys. So we can characterize the time efficiency of a randomized algorithm using the expected value. That's where expected runtime comes in. It's the expected value of the runtime. So we call this expected time sometimes. So let's say X is the time efficiency of a randomized algorithm. It's the number of steps that algorithm takes, and it does have a random aspect to it. Then the expected value of X, written E bracket X, would tell us the weighted average of how many time steps that algorithm takes to run. So this would be a sense of an average time complexity. On average, based on the random choices that the algorithm makes, how long the algorithm takes. It's important to keep track of what we're averaging over. We're averaging over all possible random choices that the algorithm could make. So the premise is we've got a algorithm like a hash table search operation, and it makes some kind of random choice, and some random choices will make it go faster, some will make it go slower. So what we're doing when we get the expected value of the runtime of the algorithm is we're adding up that expected value. So for every possible choice, the time it takes if we make that choice. Expected time is defined as follows. If the expected value of the worst case time complexity of an algorithm is x, then that algorithm runs in big O of x expected time. So for a concrete example, if the expected value of the worst case time complexity of searching a changed hash table is 2 steps, then search takes big O of 2 expected time, and we would rewrite that as big O of 1 expected time just to get the 2 out of there. So we still analyze for the worst case time scenario, but we understand that if the algorithm is randomized, the amount of time that the worst case takes depends on how the random choice goes. And so we can get the expected value of how much time the operation takes and then use big O to characterize what that is of the order of. Now, often with these operations, we analyze both the expected runtime and also the worst case runtime. So these randomized algorithms usually have two stated different time complexities, an expected time and a worst case time. So the expected time tells you the average runtime for an average random choice, and that's kind of typical, what you would typically see when you run the operation. But we will also usually state the worst case time for that operation, and that's the worst case scenario with regards to the random decisions. So that would be if you got the most unlucky random choices possible. In our context of hash tables, that would mean if you got the most unlucky hash function you could possibly get, that would give you the worst case time performance. So here's an example. This is a true statement. Searching a chained hash table takes constant expected time and big O of n worst case time. So that means on average, typically what you see is that searching in a chained hash table is constant time, very fast. However, if you get the absolute worst case scenario, it could take as much as a linear time to search a chained hash table. So since the worst case time is the maximum possible time, and the expected time is the average, the maximum is going to be greater than the average. So the expected runtime is going to be a faster big O expression than the worst case runtime. Like here, the average time or expected time is constant, and the worst case time is big O of n. That's a larger amount of time. Usually we analyze and state both for full disclosure. So if someone is contemplating using one of these randomized algorithms, they would usually like to know both of these facts. What will I typically see and what's the worst case scenario? So usually we work both of them out and state both of them. However, we focus more on the expected runtime because that's more typical. So typically in practice, that's the kind of runtime you'll have. And so often we focus on that one more than the worst case. So let's kind of put together all three types of runtimes that we've seen and kind of see how they compare to each other. So big O of 1 worst case time, if an operation takes constant worst case time, that means that it always takes constant time, no exceptions whatsoever. If an operation takes amortized constant time, that means it's constant time on average, and what we're averaging over is a long sequence of operations. This is like the vector resizing operation. Most of the vector adds are constant time, and then there's this occasional linear time resize, but if you spend long enough adding elements to a vector, the average is constant. So that means that an individual operation could be unpredictable because it's hard to know if you're going to do the resize or not. But if you perform quite a lot of operations, a long sequence of them, then the total amount of time it takes is predictable. So when I add it to the back of a vector, I might not know if it's going to trigger a resize or not. That's hard to know. But I know if I add 1,000,000 elements to a vector, how much time it's going to take in total, because I can predict how much time will be spent resizing. There's no surprise on the total for a long sequence. Constant expected time has an element of randomness to it. So each operation takes a random amount of time, but on average it's constant. Here we're averaging over all the possible random choices that the data structure could make. So it's not this predictable fast then slow then fast then slow thing like with amortized. It's a random unpredictable event. So every operation has an unpredictable random runtime. You really can't predict how long each operation is going to take, and it's also hard to pin down how long the entire sequence of many operations will take. So given these, if we have the choice, so if we're shopping for a data structure and we have the choice between a constant worst case time, amortized time, or expected time, usually our preference is worst case time we like the best, and we like amortized time second best, and we like expected time third best. And the reason is basically in how strong the guarantee is. Constant worst case time, it's always true. So no exceptions, that's a really good guarantee. Amortized time, you don't know operation to operation, but you can characterize the entire sequence of operations. Expected time is totally random. There's not a lot to go on. So that's the weakest guarantee and our least preferred operation. So here's how you might visualize these as a graph. So the red line is showing what a constant worst case time situation would be. So this is the same graph we had earlier, but with an additional line on it. So the vertical axis is time. The horizontal axis is how many operations we've performed. So the red line is constant. Every single operation is 3 units of time without fail. Very predictable. The blue line is an amortized kind of runtime. So that's this kind of heartbeat situation where you get a few fast operations and then you get a slow operation. And then you get some fast operations and then you get a slow operation. So, there is variation, but it follows a predictable pattern. And then the gold line is an expected runtime. It's just totally random. It bounces all over the place. So you really can't predict how it's going to go. It's one of these random walk kind of situations.